Wishing good morning, everyone. And right in the middle of the matter here. So recently, I was on my LinkedIn feed, and one of my connections sent me a commentary on an article that was talking about warp speed and physics. And I was like, yeah, but that's from Alcubierre's metric in '94, and that's got negative energy in it, so we're still quite far from it. But then I actually read the commentary. And that was from the National Institute for Astrophysics, and that wowed me because the negative energy constraint was gone. Next, please. In the next 20 minutes or so, I'll cover some of the literature about warp drive and how it shed a light on possible ways around the fundamental constraint of c, the speed of light. We will unpack the issues that we encounter along this journey towards warp, and then I will offer you an outline of the positive energy construction by Lentz. As this has the potential to move FTL travel to an engineering problem, it's also worth understanding that there's so much that we can see from the bridge of a notional USS Enterprise moving at warp speed. Spoiler alert, it's not what you see on TV. Next. So what is warp? It's a curvature and stress energy solidon, namely a self-reinforcing perturbation in spacetime that maintains its shape while it propagates. We're not covering general ways to travel faster than light, only ways of moving faster than light. So I am sorry for all the wormholes fan out there, and I'm a wormhole amateur myself, but no wormholes here. As it's impossible to propel matter to speed greater than c, we need to create something different. The idea is to generate a perturbation, the solidon or warp bubble, that is able to enclose a region of space-time where a payload, the starship, is able to sit and be transported across space-time. That is what is shown in a figure at the bottom right, the top hat function. That is the space-time expansion factor, following White and Davis, of a warp bubble, specifically Alcubierre's here. And we'll see this in a moment. You see there is a steep wall that is the actual warp wall, the warp region, and then a plateau that is the inner region of the bubble. This highlights a general property of warp drive spacetimes that is actually a very desirable property, namely that proper time of the spaceship is equal to coordinate time, for instance, time on Earth. To study warp drive spacetimes, we'll find very useful thinking looking at energy, and thus using the Hamiltonian formulation of Arnovit, Des, and Misner. We do this through the 3+1 or ADM formalism. That's the ds squared you see in the top row, where we foliate space-time in equal time 3 surfaces. And then we study the relocation through the shift vector Ni. Of course, the ansatz is that 3 surfaces are flat. So the Hij there are chronicle deltas. Next, please. Alcubierre proposed in 1994 a metric motivated by cosmological inflation that would allow arbitrarily short travel times between 2 distant points in space. Alcubierre metrics is what you see in the top row there, and it corresponds to setting a nx equals to ny equals 0 in the ADM decomposition we introduced just before. The enormous speed of separation arises from the expansion of space-time itself, analogously to the inflationary phase of the early universe. More specifically, the hyperfast travel is induced by creating a local distortion of space-time, as shown in the figure, where you see that the local volume expansion. Alcubierre's warp drive model produces a contraction ahead of the bubble and then an opposite expansion behind it. What is extremely interesting here is that it can be shown that the observers with 4 velocity 100 v times f, that's the ones that are in the spaceship, move along geodesics as their 4 acceleration is 0. And these observers are usually called Eulerian observers in the 3+1 formalism, as they move along normal direction to the spatial slices, you remember. The spaceship, thus, can be easily seen to move always along a time-like curve, and we can also verify that the proper time along this curve equals the coordinate time. Next. It was thought this distortion was the reason warp-drive spacetime worked. Space in front of a given region is contracted, whereas space behind the same region is expanded. In response, the warp bubble moves forward with a speed determined by contraction-expansion rate. Nattario, however, showed in 2002 that this contraction-expansion is not necessary at all, and that in particular, it is possible to construct a similar spacetime where no contraction-expansion occurs. Heuristically, one could best describe the warp-drive spacetime as sliding the warp bubble region through space. Space in front of the warp bubble may get contracted and space behind it expanded or not, depending on the details of the construction. Nattario's construction is more geometric rather than differential, and it is not as straightforward as Alcubierre is to be read. But luckily, that algebra was unpacked recently by a group in Texas, Mattingly et al., who, I would say rightly, wanted to brute force Nattario's warp drive metric into some visualization. As they say, while the mathematics of a warp drive is well developed, the mapping of space-time around warp drive remains hardly explored. Considering that a ship inside a warp bubble is causally disconnected from the exterior, computer simulations of the surrounding space-time are critical for the ship to map its journey. And you can see in the pictures here, the curvature invariant, some curvature invariant, this, namely the richest color for Nattario's warp drive. We have to get it short here. Next. There's no free lunch, though. I've taken all the bad news last for you. The first is that as we cross the threshold of the speed of light, horizons form, in the sense that events inside the warp bubble cannot causally influence events on the other side of the surface. There exists a similar horizon in front of the starship, a conical region, inside of which no signal can be received from the starship, but where points are visible from inside the warp bubble. This is called the visibility horizon. These horizon-like structures are the four-dimensional generalization of behavior originally discovered in examining two-dimensional warp drive spacetimes. These two-dimensional warp drive spacetimes contain event horizons surrounding the starship whenever it moves at speeds greater than c. The figure on the left illustrates how the half angle of these horizon-like structures grows steeply as warp speed increases. These structures are somewhat analogous to the familiar Mach cones associated with supersonic fluid flow. Next. Next, please. When we switch on quantum effects, the situation does not improve. Hiscock in 1997 first discovered in two-dimensional space-time that the backward and forward walls along the direction of motion look respectively as the future and past event horizon of a black hole for an observer inside the warp drive bubble. This means the starship's crew see a black horizon aft and a white horizon fore. It is very important, however, that the horizon first appears at infinity and moves inward as the speed is increased. Unfortunately, it comes very close very fast, as the singularity is located at a R star such that f of R star equals 1 minus 1 over v, with f being the top hat function that we saw at the very beginning. Remember, the top hat function is 1 inside the bubble and 0 outside, and grows steeply inside the bubble's wall. This means the horizon is at infinity when v equals 1, meaning at the speed of light, because it's 1 minus 1 over v. So with v equals 1 is 1 minus 1, and thus 0. But as soon as v grows greater than 1, the horizon appears in a counter image of that value inside the warp bubble, inside the warp walls, up to arriving at its inner boundary for v equals infinity. The central region of a warp drive behaves like the asymptotic region of a black hole. In both of these regions, the static energy density, the one that is dashed, the solid line in the figures, vanishes. You see it from the lower row, and the whole energy density is due to the Hawking radiation generated at the black horizon in the back wall. The formation of a white horizon produces a transient radiation, which accumulates on the white horizon itself. This causes the energy density, the total energy density, to grow unboundedly with time on this horizon. And thus, the semi-classical back reaction on the renormalized stress energy tensor will make this superluminal warp drive to become unstable in a time scale of the order of the inverse of surface gravity on the white horizon. That's roughly the inverse of the temperature. There's also a Cauchy horizon, that's wrong in the slides. It's a Cauchy horizon producing infinite blue shift of the black horizon Hawking radiation. Next. And last and the best, negative energies. We start with energy density, bottom left, 8 pi E equals 1/2 of that, where we have already projected the Einstein equation onto the hypersurface normal. We're working still in the idea that we're slicing space in equal time slices. The geometric side of the energy constraint equation is divisible into the intrinsic hypersurface curvature, that's R3, the extrinsic curvature trace, Kii, and its quadratic hypersurface scalar, Kij, Kji. As we want the Hij metric of these foliations to be the Kronecker deltas, so be flat, the intrinsic curvature R is 0. All the three Alcubierre, Nattario, and Lentz constructions can be classified through the characterization by a shift vector potential function, namely a function phi with spatial gradient related to the components of the shift vector. So each component of the shift vector n is the derivative of phi. Imposing a relation between all the shift vector components makes the trick. The most common relations explored in literature are linear and elliptic. Specifically, the linear relation is Alcubierre's warp drive spacetime. That's nx equal ny equals 0. And we get the result in the bottom center. And that is actually a toroid of negative energy perpendicular to the direction of motion. That's the figure on the top. You can imagine that the motion is happening from left to right. So it's towards your right. The spaceship is flowing towards your right. So you see that in Alcubierre's warp drive, the sources of the shift, that's these negative energy toroid, are completely out of phase with respect to the expansion contraction factors that were forward and backward. The zero expansion feature of Nattario's construction is captured by the elliptic relation divergence of n equals 0 and restricts the energy form still to a negative quantity. Francisco Lobo in 2017, and again Alcubierre in 2021 tell us that we need energy m warp of the order of minus v squared r squared times sigma. That's basically the inverse of wall thickness. So you see that there's a component of the wall thickness in the quantity of negative energy that we have. To recover the
Dr. Rizzo, Stephen, just letting you know, we're on about a 3-minute warning. If you could kind of get to your last slide, we've got a lot of questions coming in. Thanks.
All right. Okay, so next one. So we can have a positive energy construction if we look at the construction of the energy constraint. You see that there's a possibility to have an island of positive energy configuration by arranging a suitable potential. Next. And that's the soliton. And the Lentz soliton has a lot of considerable and remarkable properties. This is a soliton for traveling at warp 2 from Star Trek, namely 10 times the speed of light. The configuration is such that the wave fronts you see in the bottom center, that's the density of this hyperbolic sources. They're arranged in this diamond shape configuration. You see that the energy is practically overlapping to where the sources are. You see that the shift, so the tidal forces allow for a high and level center zone that's practically tidal force free, and in the top center figure in the left one, that's the shift towards the front, that's the Z shift. Blue is in forward and red is backward. You see that there's still there is a wide area where we have strong push in the front. This construction still has time that is equal to coordinate time, so still very remarkable. And the energy quantity can be shown so that an energy for a bubble of air of R 100 meters and wall thickness of 1 meter is 0.1 solar masses. And this brings a lot of other consequences to the constraints that we saw before, for which we don't have time to discuss. So very open to questions.
Thank you, Gabriel. We have quite a few questions, and so these are good ones. But let's start with: could a warp bubble propagate at superluminal velocities, or might there be a maximum propagation rate, perhaps at C?
No, the warp bubble is space-time itself. There's no propagation. There's a region of space-time that is moving across space-time. It's like with inflation. You don't have a upper speed boundary when it comes to inflation. It's space-time itself that is moving. You don't have propagation inside space-time. So there's no upper boundary to the speed that we can achieve with this construction, relatively to fundamental constraints like C. There's other problems with horizons, with semi-classical instability, with mass energy components, and a lot of other stuff, but we're not in principle bounded by speed.
Thank you. Would space being discrete pose a challenge to creating a warp drive?
No, I would say no, because there's a couple of answers here. This is not a construction that relies on a quantum structure of space-time, so it's a classical construction. Having a high energy cutoff like strings or loop quantum gravity may improve issues with negative energies. I think there's a paper of 2002 where there's a good discussion on on how the energy conditions are basically moribund. and how this needs transition to a new and now widely accepted idea of quantum inequalities. But I would say, no, I don't think so.
Okay, great. And finally, could the trajectory of a warp bubble be affected from within the warp bubble?
No, it can't, because you're causally disconnected. The inside of a warp bubble is causally disconnected to the outside of a warp bubble. So the only thing it can be driven as long as so there's no way you can decide where to steer depending on the information that gets to you. But you can modify at a certain time the charges and the sources of this deformation so that you can actually steer or change the trajectory. That you can do, but you have horizons in the back and in front of you. So you cannot react to anything that comes to you. And that made me think of when in Star Wars, actually, there's the whole idea of hyperspace. But when they're doing the computations to do the hyperspace jump, and all these computations remind me of we need to waypoint our trajectory because we cannot control our trajectory reactively. We can only plan for it in a warp bubble.
Thank you.